My name is Bob Cheesebrough, and I'm a technical consulting engineer in Intel's compiler team. Welcome to the fifth in a series of videos covering Intel compiler vectorization essentials. In this video, we will explore what SIMD-enabled functions are. On this slide, we will do a quick overview of SIMD-enabled functions. SIMD-enabled functions allow user-defined functions to be vectorized when they are called from within vectorized loops, or are called with array notation arguments. The vector declaration and associated modifier clauses specify the vector or scalar nature of the function arguments. SIMD-enabled functions are supported by both Intel SOAP Plus and OpenMP 4.0. This is a very simple example of providing vectorized user-defined functions called SIMD-enabled functions. It was designed with legacy scalar code in mind, so the idea is that we annotate a legacy-style scalar function that takes single values as arguments and which returns a single value as a return. This legacy function would have been called from within a loop. So here we are modifying the scalar function foo. Foo is like a simple device function or shader kernel working on one element at a time. For IA, we'd like a version of foo that works well on SIMD vector. SIMD-enabled functions is Intel compiler's mechanism to get that to happen. We see three usage examples here. Two of them will call the vectorized foo, while one calls a scalar version of foo. The fact that the compiler generates multiple versions behind the scenes means that if I call foo from some module that still treats it in the old scalar way, the function call works just as it did in the old scalar days. But for modules which have been updated to treat the function as a vector function, by passing it arrays of values or by calling it from a SIMD loop, we would get a vectorized version of the function. This all is seamless to a developer who does not need to remember different names for different functions. SIMD-enabled functions allow the programmer to use scalar syntax to describe an operation on a single element, then apply that operation to arrays in parallel, utilizing both vector parallelism and core parallelism or threaded parallelism, similar to the CUDA OpenCL style kernel functions. The programmer's responsibility is to write standard C++ functions with a scalar syntax, then annotate them with #pragma OMP declares SIMD, using one of the parallel syntax choices to invoke the function. Then you utilize appropriate modifier clauses for the vector attributes, and then you invoke the function to operate on arrays of arguments rather than scalar arguments. The compiler's responsibility is to generate short vector versions of the function that can operate on multiple elements at each invocation. It also generates a scalar version that can be called by single iterations of a scalar loop. It invokes the function iteratively, applying multiple elements at a time until all elements are processed. The developer declares a function to be SIMD-enabled using OpenMP 4.0 as follows. Use the #pragma OMP declares SIMD clause. The declare SIMD clause means that all arguments to the function are treated as vectors, and the return is treated as a vector. This is the default behavior. The developer can deviate from the default behavior by specifying modifier clauses. It is recommended to add the SIMD-enable directive to the function prototype, also called the header file. Now let's take a look at some of the OpenMP SIMD modifier clauses. The modifiers for #pragma OMP SIMD are similar to, but also in some ways distinct from, their #pragma OMP SIMD loop counterparts. The uniform clause indicates a variable or array or pointer that the developer assures will not be changing once the function is entered. The syntax is uniform, then with a list of parameters. Shared scalar parameters are broadcast to all the vector lanes. The linear describes variables that will be incrementing monotonically, such as loop induction variables. The syntax is as follows. Use the linear, then give the parameter with its optional step size. The SIMD-len argument represents the largest integer for a vector that the compiler is free to assume, usually something like 2, 4, 8, or 16. It can be given explicitly as in the SIMD-len num clause shown here. The aligned clause tells the compiler that the byte alignment is of a list of memory locations. Usually the byte alignment is 4, 8, or 16 bytes. The type of list items appearing in the align clause must be arrays or pointers, or references to an array, or a reference to a pointer. The modifier indicates that the programmer has taken steps to ensure that the first element, element 0, of an array has an address that is aligned to a specified byte boundary using something like mmmalloc, for example, to specify the alignment of the data. This allows the compiler to use aligned vector loads, which are faster and more efficient than scalar loads or unaligned vector loads. For more information, refer to the OpenMP 4.0 specification. Why do we need the uniform and linear modifier clauses? Because unless modifiers, such as uniform or linear, are specified, then each parameter to the function will be treated as a vector. This can be very wasteful in that the entire vector must be passed as an argument, sometimes needlessly. Study the example in the green box. Using the uniform clauses, we can specify that all vector lanes will share a given variable. In this example, all the vector lanes share a copy of the base address of A. The linear clause tells the compiler that it can assume that the variable I is used in a monotonically increasing fashion, with stride 1 in this case, so multiple copies of I do not need to be passed to the function as a vector. For a more detailed exploration of this topic, read the following article on software.intel.com entitled Use of Linear and Uniform Clause in Elemental Functions. Now we are going to discuss ways to invoke a SIMD-enabled function. To start off, we are going to want to invoke the SIMD-enabled function called mySIMDF, defined in the green text box. So let's take a look at the top line in the invocation example table, with the standard for loop. You would invoke the regular old scalar version of the function, mySIMDF, just by calling the function, passing it in an array, and it will compute it element by element, iteration by iteration. So in this top line, please note that we are just calling the plain old original scalar version of this function, which has been generated for you by the compiler behind the scenes. The compiler will generate at least one scalar version of this function and possibly several vectorized versions. We can invoke the OpenMP declared SIMD version of the function in a couple of different ways. You could call mySIMDF from within a pragma OMP SIMD loop as seen on the second line. The compiler then looks at this and says, I see what you mean. You're passing me an entire array or vector of elements to mySIMDF, and you want me to vectorize this function so that the enclosing loop can be vectorized. The function will then return an entire vector of values back to the call site. Note that pragma OMP SIMD is not always required. The auto-vectorizer may go ahead and vectorize this for you, but pragma OMP SIMD ensures vectorization. Another way that mySIMDF could be invoked is with array notation, as seen in the bottom line. Again, the compiler will cause the SIMD or vector version of the function to be called so that entire arrays can be passed in, operated upon, and then passed back out of the SIMD function. These are examples of how SIMD-enabled functions can be invoked within your code under different programming approaches.
This concludes our 5th video. Please take a few minutes to watch our next video in the series, Performance Essentials 6, where we will explore OMP declares SIMD call site dependence.
Here are our requisite optimization notices and legal disclaimers.